Welcome to the pSemi sNpViewer. This tool allows you to view S parameters in various formats with data loaded from either Touchstone or MDIF files. It's available as a free download from the pSemi website. Just follow the QR code. Firstly, I'm going to show you some basic features. Next, there will be a short video on loading, displaying different formats, saving the state, and outputting the data in pivot table format. Hello and welcome to pSemi sNpViewer basic features. We'll just load up a couple of files, maybe 6 files from a folder. This one is files from a DSA, a digitally switched attenuator, and you can either load up one file or you can control click or shift click, and here we are loading 6 files. And that happens pretty quickly. Just show log magnitude. Okay. You can use this button to load all files from one folder. In this case, there are 128 settings for the DSA, so that's 128 files. So if we look at S21, which is the insertion loss, and you can see the DSA and how it operates. We can change this to color if it helps. Takes a while longer to plot, but it can be useful in this representation. If you want to look at S11, perhaps just for one file to be clearer, there's S11. We can look at the same, so that's in Smith chart representation. We can look at it in polar representation, which is in fact the same plot but on different axes. And we just showed log magnitude. That's just for one file. Phase response, that's the phase response from one end to the other. Log mag versus phase, we'll come back to that later. Delay, group delay is also shown. Time domain impulse response. This can be quite a useful plot. So this is the response from one end to the other of the device. If you put a pulse through it, there's a control here, and we can change the width of that pulse and the time span. So let's say 100 picoseconds time span and 100 picoseconds bit period. And this is the time domain impulse response through the device. So that uses an inverse FFT. Let's go back to S21 log magnitude. We can generate a pivot table, so this would go to a CSV file. So let's select all the files. And then this button here will allow us to output data pivot the selected data or pivot all the data. I've selected it all, so, and then it would just come up with a file save box, which I don't need to do. And the one very useful feature is being able to save to a save state file. So when you do that, all the data that you've imported is saved within the save state file for recall later. And then you can just load it back using that button. I'd like to show a few examples where the sNpViewer can be used, and also take the opportunity to showcase a few pSemi newly released products. So firstly, I'll show you the PE42444 high power SP40 7 GHz switch, which can handle 10 watts RMS, 100 watts peak. Then I'll show you the PE42445, which is a high isolation SP40 8.5 GHz switch, which can handle 64 dBs of isolation at 4 GHz. And finally, I'll show you the PE423211, which is an IoT SPDT switch up to 12 GHz. It has an incredibly low supply current of 90 nanoamps. I'll just show you a few examples of some pSemi products, just some RF switches. We'll look first at PE42444, which is a 100 watt peak, 10 watt RMS SP40 switch. So as it's an SP40, there are 5 ports in total, including the common, so it's S5P files. Each file represents a different port being switched on. So with RF1 on, we look at S21, and we can look at the insertion loss in log magnitude. So this is, as I say, this is a high power switch, so the insertion loss is very low. And you see a sort of knee above 5 gigs, but even at 7 gigs, even at 8 gigs, it's still usable, as the insertion loss is still below 2 dBs. So we can also look at, let's look at RF2, check that that's the same sort of answer, S31, and we get the same sort of result. We look at the insertion, the isolation. So with RF2 on, we'll look at S21, and this will give you the isolation from RF1 to RFC. Let's look at a high isolation switch. We'll look at 42445. Again, 4 S parameter files, each one for RF1, RF2, RF3, RF4 being enabled. So let's look at S21. We'll just look at the insertion loss with RF1 enabled. So the insertion loss goes somewhere between half a dB up to even at over 8 gigs, we've still got less than a dB of insertion loss. It's a very good part. But the selling point on this part is the isolation. So if we look at S21, so that's RF1, but we switch on RF2, we can see the isolation. And you can see here that even at 6 gigahertz, we've got 55 dBs of isolation. and to a maximum of 70 dBs of isolation. So it's a pretty impressive part. This. Last part we'll look at is an IoT switch. Let's load that one up. So this switch is a very low current battery powered, for battery applications switch, because the supply current is so low. So let's look at S21 with RF1 enabled. I'll just draw a box around that so that we can see it greater resolution. So 10 gigs, so this is about 12 gigs, and we're just over a dB of insertion loss at 12 gigs. So it's a very wideband switch. In fact, we called it an ultra wideband switch. It's just an SPDT, very small footprint. Let's look at the isolation. So with looking at our port 1, but with port 2 enabled, we can see the isolation. So even at 10 gigs, we've still got over 20 dBs of isolation. Thank you. One useful feature of the sNpViewer is being able to create lookup tables, which are used by one's host processor to optimize the phase or amplitude settings. This is the process for creating a lookup table. S-parameter files for each setting are loaded and assigned to a point on a grid, and as each file is imported, it's assigned the closest point on the grid for each chosen frequency. If a closer point is found, the previous point is then discarded. The process can take a few hours, depending on how much data you've got. Imported data can then be saved to a lookup table file in CSV format. Thing to note here that settings cannot be saved in touchstone files in a formal way. So the best way we have found is to use the file name to save the settings. The CSV file afterwards must be edited to separate out the settings. Before importing the data, we're going to need to know the full amplitude control range. I find the best way to do this is to import all the data and display it in this format, logmag versus phase. Here we see the maximum amplitude is -9 dBs and the minimum is -24 dBs. In my application, I'd like a little bit more margin at the top end, so I'll be using -10 dBs at the top, and I'll request a dynamic range of 16 dBs in 64 steps. These are the numbers that I'll be using when I perform the import into the grid next. Hello, this is the pSemi sNpViewer lookup table creation tool. We use this button to load all files from a particular folder. The device I'm looking at is a phase and amplitude controller, and this folder contains settings for 256 phase settings and 256 amplitude settings, making the total 65,000 files. We're going to import them all, and it's going to analyze each file. Now, because there are so many files and frequencies, it might run out of memory, so we just select a subset of the frequencies. Save memory. And this is the grid that we are going to form. It's going to be a 1/4 dB step size, and I already know that we want to take it from magnitude -10 to -25.75 in 64 steps. It's worth noting at this point that you can disable either phase and just do amplitude, or you can disable amplitude and just do phase. But in this case, we have a phase and amplitude controller, so we want to do both. We'll start the process. So as you can see, it's hunting through all 65,000 files. As it builds up, these points are assigned to a grid point, and if a better solution comes along, then each point gets replaced. So it's going to take an hour or so to do that. This display is just at 6.5 gigahertz, but you can change the display. It's just for monitoring progress. All the data has now been imported and sorted. Let's just check it. So if we select S21, log mag versus phase, and we'll just do it mid-band. We'll take a moment to plot. That looks a bit like a grid, so I'm happy with that. Let's save the state. This would be a good time to do that. Now we want to output a lookup table, but before we do that, the lookup table is only generated for each frequency that is selected. So we want to do it for all frequencies. So we need to click all frequencies, which unfortunately will take a moment to replot. If the viewer gets into a cycle of replotting and replotting, just simply click away out of the window. That's done, so now we can save a lookup table. It's the first item in the list. These settings should be correct. And lookup table is now saving. And then it just will replot. We now have a lookup table, but there is a problem. The setting for each requested phase and amplitude is shown as the file name. This is because there's no official place in Touchstone format to store settings. So the way we deal with this is to store the settings to the file name, and I would recommend people to do the same. Here I have used the tick mark to separate each field. So with this in mind, we can use the tick mark to separate the columns. So firstly, make space for the extra columns, 3 in this case, using insert columns in Excel. and then select the file setting column and use the feature text to columns to separate the columns using the tick mark as the delimiter. The lookup table is now ready for final editing before use. Put discreetly in the same folder as the sNpViewer tool, you will find snp_merge.vxe. This tool is used for merging collections of smaller touchstone files into a larger one. For example, here is the process of building a set of S5p files from multiple sets of S4p files. Why do I need this? Simply because I only have a 4-port VNA, but the part I'm measuring has 5 ports. Here I've shown how the S4p files are put together to build the S5p files. On the right you can see how each collection is measured on the 5-port device. Please note that if you have 4 settings, for example, each collection can contain 4 files. And then when you save, it will generate 4 S5p files. Here's another example. This is used to build an S7p file from multiple S4p files. And this would generate S9p files from the S4p files. And finally, this would be used to generate S13p files from multiple S4p files. Thank you.